Assalamualaikum and good day to everyone. Today we continue with two component system, vapor pressure composition diagram, boiling point composition diagram, and non-ideal solution. This is vapor pressure composition diagram for ideal solution. Suppose you have an ideal mixture of two liquid A and B. This is axis Y. This is axis X for mole fraction. Axis Y for vapor pressure, and then you draw another line. Axis Y, this one is vapor pressure. So from equation, the partial vapor pressure of A at particular temperature is proportional to its mole fraction. So you draw the straight line. So you label here vapor pressure for pure A. Okay. So this one is mole fraction 1 and this one is 0. Mole fraction for A. Okay, so because the partial vapor pressure of A is proportional to its mole fraction. So do the same thing for B. Okay, so this one will be 0, this one will be 1. This mole fraction for B. Label here vapor pressure for component B. So as you can see from this diagram, the mole fraction for B decrease as the mole fraction of A increase. So as the mole fraction B decrease, the vapor pressure of B also decrease. So vapor pressure of pure B is higher than that of pure A. That means that molecule must break away more easily from the surface of B than A. It is due to the intermolecular forces are relatively weak. So this indicates B is the more volatile liquid. So to get the total vapor pressure of the mixture, you need to add the value of A and B together at each composition. So you will get straight line as shown in the diagram. So this is total pressure for the mixture. Vapor pressure composition curve for ideal solution. The figure shows the equilibrium between liquid and vapor of an ideal solution. Example, the mixture of benzene and toluene. Axis Y is for vapor pressure. Axis S is for the mole fraction for A and B. Liquid is favorable at higher pressure. Vapor is favorable at lower pressure. In this region, it has two phases, which is liquid and vapor in equilibrium. This line tells us the composition of the liquid. This line tells us the composition of vapor. If let's say the liquid at C1 boil at this temperature T1, it will give you a vapor with composition of C2. So composition of vapor is much richer in B, which is the more volatile component. So you boleh nampak kat sini, the mole fraction of B is increased, meanwhile the mole fraction for A is decreased. And this is the vapor pressure composition curve for benzene toluene mixture. So we start with the boiling point of pure benzene and toluene. So benzene will have the higher vapor pressure. That means that it will have the lower boiling point. Similar to toluene, it has lower vapor pressure, so it will have higher boiling point. Okay, so this line tells us the composition of liquid and this one tells us the composition composition of the vapor. If you boil a liquid mixture, you would expect to find that the more volatile substance escape to form a vapor more easily than the less volatile one. So in this diagram, you would expect to find a higher proportion of benzene, the more volatile component in the vapor than in the liquid. So when more fraction of benzene is at C1 in the solution, boil at this temperature, T1, it will give you a vapor composition of benzene at C2. As liquid composition of benzene increase, its vapor composition increase even further. So for example, if C3, liquid at C3, boil at this temperature, so it will give you vapor composition at C4. So you akan nampak bila liquid composition of benzene increase, the vapor composition also increase. And then this one is more fraction for benzene. This one 0, this one 1. And then more fraction for toluene, 0 and then 1. And increase in benzene composition, the composition of toluene also can decrease. Boiling point composition curve. The figure shows the equilibrium between liquid and vapor of an ideal solution. Example, mixture of benzene and toluene. Ini part C Y, kita plot temperature degree Celsius, and this one also kita plot temperature, and then this one is part CS, kita plot sebagai composition of benzene ataupun toluene. Okay, boiling point of benzene is lower than toluene as benzene is more volatile than toluene. Okay, this is due to benzene has high vapor pressure. It means that the molecules are escaping easily from the surface, which means that the intermolecular forces are weak. So you don't have to supply so much heat to break them and boil the liquid. So that's why benzene has lower boiling point. So the diagram is upside down because the vapor phase is stable at high temperature. Okay, so ini vapor phase, ini liquid phase. So any line at the boundary curve, this one, tell us the composition of the liquid. And then this line tell us the composition of vapor. So all you have to do is to use the liquid composition to find the boiling point of the liquid and then look at what the vapor composition would be at that temperature. So let's say the liquid benzene with composition L1 boil at T1, giving a vapor with the composition of V1. So vapor at V1 will condense to give a liquid of composition of L2. This liquid of L2 will in turn boil at lower temperature T2 and give out a vapor composition have at V2. Maksudnya dia akan richer in benzene. So if you keep on doing this, okay, so dia akan condense V2 ni, dia akan condense to give liquid of composition of L3, and then this liquid of L3 will in turn boil at lower temperature T3, so dia akan give the vapor composition at V3. So if you keep doing this, you will eventually get pure benzene. So component that has higher vapor pressure has lower boiling point, and component that has lower vapor pressure will have higher boiling point. So the most volatile compound will distillate first as it has lower boiling point. Non-ideal solution. At low concentration of solute, most solutions show deviation from ideality. Non-ideal solution can deviate from ideal behavior in two ways: positive deviation from Rod law and negative deviation from Rod law. The deviation of real gases from ideal gases behavior is caused by two factors, which is the existence of intermolecular forces of attraction between gas molecules, and the second one is due to the gas molecule occupy space, which is they have volume. Deviation from ideality. Extreme deviation from ideality will result in maximum or minimum in vapor pressure diagram and temperature composition diagram. This will produce azeotropic mixture. Okay, so mixture of two miscible liquid that has a constant boiling point and the vapor that exists in equilibrium with the liquid has the same composition as the liquid. So on heating an azeotropic mixture until it's boiled, the vapor liberated has the same composition as the original liquid mixture. So maksudnya the mixture of two or more liquid whose proportion cannot be altered or changed by simple distillation or cannot separated completely. There are two types of deviation from ideality. The first one is positive deviation and second one is negative deviation. For positive deviation, vapor pressure is higher than ideal in this mixture, means that the molecules are easily broken away than they do in pure liquid. That is because the intermolecular forces between molecules of A and B are weaker than they are in the pure liquid. So the vapor pressure is higher than predicted by Rod law. Maksudnya the tendency of molecule to vaporize is greater. So the boiling point is lower than its pure component. And then for negative deviation, vapor pressure is lower than ID in this mixture, means that the molecules are not easily breaking away than they do in pure liquid. That is because the intermolecular forces between molecules of A and B are greater than they are in the pure liquid. So the vapor pressure is lower than predicted by Rod law. So maknanya the tendency of molecule to vaporize is lower. So that's why the boiling point for negative deviation is higher than its pure component. Y axis is the temperature, and then X axis is the percentage composition of pure A or pure B. So we have here 1 mole of pure A, 0 mole of pure A, so mole fraction for A, and this one we have 0 mole B and 1 mole pure B. So this one for mole fraction for B. Positive deviation means that the mixture has higher total pressure than the vapor pressure of either pure A or pure B. They have higher escaping tendency from liquid phase to vapor phase due to weaker intermolecular attraction between A and B than those existing in pure component. So that's why their boiling point is lower than its pure component. And meanwhile, for negative deviation, the it means that the mixture has lower total pressure than the vapor pressure of either pure A or pure B. They have lower escaping tendency from liquid phase to vapor phase due to stronger intermolecular attraction between A and B than those existing in pure component. So that's why their boiling point is higher than its pure component.